2 points in a neuron. We have the cell body here and the dendrites. We have our axon hillock, and then we have the axon. Oh, this is a dead one. Alright, so that's the axon. Graded potentials are decremental. That's what's being shown here. Positive charges enter the cell, you get a depolarizing graded potential or local potential. It's the same thing, used interchangeably. But the charges are disappearing. Why are they disappearing? Because they're diffusing away from each other, so the concentration is going down. And also the ATPases are pumping them back out. So decremental. We also have a decremental hyperpolarizing local / graded potential. And that's where negative charges are accumulating in the cell. In the cell body and dendrites, you can have depolarizing graded potentials. You can have hyperpolarizing graded potentials. Depolarizing graded potentials, you can have an increase in you have to have an increase in positive charge. So right now you only have 2 ions, well actually 3, that you have to think about. Sodium, if sodium comes in, so increase sodium inside the cell, you have a depolarizing graded potential. If you decrease potassium leaving the cell and the ATPase is pumping it back into the cell, then you get positive charges not leaving plus re-entering via the ATPase. You get depolarizing graded potential. Since chloride is normally leaking into the cell, if you decrease the entry of chloride going into the cell and the ATPase is pumping it out, then you have negative charges leaving the cell and not entering the cell, which leaves positive charges behind. So depolarizing graded potentials can be occurring due to a decrease in the permeability of a negative anion, like chloride, a decrease in the permeability of a positive anion that's more concentrated inside than it normally is outside, so closing potassium channel, or increasing the permeability of a positive ion. So you're going to have depolarizing graded potentials. You're also going to have hyperpolarizing graded potentials happening at the same time, but in different locations in the cell. You have to remember that this neuron, this postsynaptic neuron, is receiving input. All these dendrites, the soma, all that surface area there is going to receive input from other neurons that you don't see in the picture. If you look at the cell body of a neuron in Martini, so flip back to the neuron chapter, you're going to see that there's probably 1,000 other neurons that are impinging on this neuron. Some of them are going to be excitatory, some of them are going to be inhibitory. How you stimulate these upstream neurons determines whether you get a lot of depolarizing potentials or a lot of hyperpolarizing potentials or equal numbers and total cancellation. Okay, so you think if you depolarize with an increase is sodium going into the cell. How do you hyperpolarize with sodium?
Too much oil when you're repolarizing.
Decrease its entry. Why does that hyperpolarize? Why does that leave negative charges behind? So if you decrease sodium in, why does that leave negative charges behind? Why does a decrease in sodium and potassium going out or a decrease in chloride going in cause positive charges? Well, potassium is a positive, but chloride's not.
But it's the same. That's 70.
We can ignore it for purposes of resting membrane potential. Decreasing chloride's permeability, so it's not going in. So why is that causing positive charges to accumulate inside? The negative charge isn't going in. Doesn't bind. No, I think you're off track.
Is the one chloride ions on the outside causing the positive to activate?
No. As they're negative inside and they can't leave, they can't move. So the anions on the cytoskeleton, they're not contributing to anything about that chloride ion. What are you forgetting about? I heard somebody say sodium and somebody said what is sodium?
Channels.
Sodium?
Channels.
Yep. Not a sodium channel. Sodium, potassium, pump, ATPase. If you've got a sodium potassium ATPase, you probably got something handling chloride that's an ATPase. If it's diffusing in down its concentration gradient, you've got to get it out to maintain its concentration gradient. Going up the concentration gradient to get it out is going to be active transport to get it out. So if you decrease the permeability of chloride entering, but your ATPase is still pumping chloride out, the normal leak in isn't there, but the efflux is still there. You leave positive charges behind as you pump the chloride back out. So sodium, how do you hyperpolarize it? You decrease its entry, but what's still going on? The pump, pumping it out. 3 sodiums go out. You're bringing potassium in, but there's only 2 potassiums coming in. So overall, you're pumping more positive out than is coming in, and that leaves a negative charge inside. So decrease the permeability to sodium, or what do you do to potassium? How do you get negative charges to accumulate in the cell manipulating potassium? Increase potassium leaving. That's supposed to be a T. So have potassium leave faster. How do you do it with chloride? Probably not that. You could poison the pump, but then it'd never work for you again. So what are you going to do that won't damage your cell? Won't irreversibly change the function of your cell. It's a reversible change. What do you do for chloride? Increase chloride movement in. So increase chloride in. So if you look at this, they're opposite, right? So you can memorize that, or you can think about it and understand it logically. If you want to accumulate negative charges inside, you can do that by having more negative charges enter, or you can have more positive charges leave, and that would be that scenario, or decrease the permeability of a ECF positive charge, and then have it be pumped out on a regular basis anyway. So as the positive charges leave, it leaves negative charges behind. We've got depolarizing in some areas, you've got hyperpolarizing in other areas. The negative charges diffuse, positive charges diffuse away from each other. So concentration of that charge is decreasing, concentration of this charge is decreasing. When they meet up, they cancel each other. When they find their ATPase, they're gone. So we have charges dissipating. You have to sum the charges at this first part of the axon. Think about the names for that region. Axon hillock is just a very ancient term describing what it looks like. It has nothing to do with its function. The other two names for this region tell you about what's happening here. So one name is called the trigger zone. What is it triggering? It's triggering action potential. The other name is initial segment. This tells you it's the initial segment of the axon. So what is occurring here is going to be replicated along the axon. Trigger zone means what's occurring here is going to allow for the action potential to be generated in this region first, and then the events that occur here will be repeating as you go down the axon. The nerves that come in here and inhibit, shorthand for inhibit looks like capacitor plates in physics. Shorthand for excitation, your book uses an arrow. Some books use a forked tongue like a snake. Those, whether your fork is looking like an arrow or a snake's tongue, they're excitatory. So the neurotransmitter is released here that bind to receptors in the membrane. If the nerve is releasing a neurotransmitter that causes positive charge to accumulate inside, it's creating a depolarizing local potential or graded potential. If the receptor that's binding the neurotransmitter from here causes, I drew it in a circle, sorry. The receptor should be, let's just put it on a dendrite that comes out. Solve the problem there. Okay, so negative charges accumulate inside the cell body. Then you have a hyperpolarizing potential. 3 ways you can do a hyperpolarizing, 3 ways you can do depolarizing potential. The events that occur here, outside the trigger zone, outside that initial segment, all those events are due to neurotransmitter binding to a receptor. So these are ligand gated channels. So you have to have the ligand bind to the receptor, and then events change within the cell. What you have at this trigger zone and initial segment are not ligand-gated channels. They are voltage gated channels. You have two kinds of voltage gated channels, sodium and potassium. They're both located in this initial segment. So you've got sodium channels, and next door or around it you'll have potassium channels on both sides. So let's do two sodiums on this side, one potassium on that side. And they'll be around throughout the whole surface area there. What triggers, where does the voltage come from? It comes from all these ions that are moving in the cell body and the dendrites. As they diffuse away and cancel each other out, if there's enough coming in that is positive, and you get those positive charges to reach this initial segment and get to threshold, then you can open voltage-gated sodium channels. So action potential, everybody knows we're on chapter 4, right? People who come in late can guess. Okay, so action potential. We've got graded potentials that are depolarizing, graded potentials that are hyperpolarizing. If we get a lot of graded potentials in the cell body, but those charges dissipate, and by the time you get to the trigger zone, you have lost enough charges so that you're below threshold, then what happens?
No action potential.
Nothing happens, right? So you have to be at threshold, you have to reach the threshold, or be above the threshold to trigger an action potential. So all these graded potentials, if you get to threshold, so what's your resting membrane potential that they're talking about for neurons? Minus 70. So resting membrane potential is not going to change if you are below threshold when you get to the trigger zone. If you get so much positive charge that when it degrades you're above threshold at the trigger zone, then you're going to see the resting membrane potential. It's at the trigger zone. As this is coming down, this is starting to rise. And at this point, where the two lines intersect, you're above threshold. So at the time that you cross the threshold point, instead of tapering off of that, the opening of the voltage-gated channels, you get almost a straight increase in charge. So there's so many sodium channels opening in that initial segment, sodium rushing in, that the membrane potential pretty much takes off in a vertical direction. There's a little slope to it, but it's almost straight up and down. It's just slight slope. At that point where the voltage gated, e.g. sodium channels open, you get a large influx in sodium. You remember the conformation. Here the channel has an internal gate that's closed, and you have an external gate. This activation gate is closed until you reach threshold. Then this gate opens. Now you've got a channel, and sodium is rushing in. A lot of sodium rushes in. So positive charge, instead of working its way up with a fairly flat slope, suddenly the slope of the line almost vertical. When you reach plus 30 millivolts, there's enough positive charge inside the axon at that initial segment that the positive charge accumulating here is going to repel the positive charge on this protein. And the negative charges that are out here now, because sodium left, are going to attract that part of the protein. And at this point here, you are now going to have the channel closed by the inactivation gate. So that little ball will come up here and sit in the channel. So the positive charges here on this part of the protein are getting pushed, they're getting repelled by the sodium that comes in with that positive charge, and they're getting attracted to the negative charges outside. So sodium channels close at plus 30 millivolts. When sodium channels close, what is still going on in the neuron with regard to sodium? It's not entering anymore, but what's happening? Eric.
What's the question again?
Okay, sodium channels are closed, sodium can't enter, but what else is happening to sodium in the rest of the membrane? Now I got two Erics. Okay, so I asked Eric, so let him answer, and then if he doesn't get it, you can have.
Didn't we come back
it.
and
Yes. Yes. You have the sodium potassium ATPase pumping it back out. So what's going to happen to the charge inside the cell? It's going to start to go down. You're starting to repolarize. Part of that is because sodium's not entering, but it's getting pumped out. One other thing, what other channels do we have in this area? Potassium. So when you open a potassium channel, what happens to the charge within the axon? Okay, you're telling me what happens, but I'm asking you what happens to the charge inside the axon? Becomes more negative. Why? Because potassium goes out. Why does it go out? Down its concentration gradient. It's going to be attracted to the anions in there, but it's going to leave. So voltage-gated potassium channels. Somewhere after the closing of the sodium channels, or exactly at that point, I don't know if they agreed about this, but at the point where sodium channels close, or just slightly after that, then potassium channels open. Potassium channels, simple channels, they're either closed or they're open. You got no activation, or you have an activation gate and it's either closed or it's open. So potassium gates are opening probably, but even if it's not, just think of it. You get to plus 30, then potassium gates are going to open. You get to plus 30, sodium inactivation gates are going to close the sodium channel. At that point where we have that much positive charge in, you close the sodium channels, sodium's getting pumped out by the ATPase. You open potassium channels, and potassium is leaking out, which leaves negative charges behind. So ATPase, you open the sodium channel, and the ATPase, after sodium comes in, it's pumping it right back out. As you are opening the sodium channel, what's happening to potassium due to the ATPase? It's getting pumped in. So sodium's coming in and potassium's coming in due to the ATPase. That helps you accumulate positive charges even faster. And also accumulate negative charges outside even faster. You don't have to move a lot of charge. You just have to move enough charge so that the outside of the membrane now becomes negative and the inside of the plasma membrane becomes positive. When this happens in the initial segment, you get sodium diffusing back into the cell body. You get sodium diffusing down the axon. The voltage increasing here, is that going to have any effect on the cell body? No. These are ligand-gated channels. That voltage change doesn't affect them. Only neurotransmitters affect them. The only thing the positive charge diffusing back into the cell body could do is if you get more depolarizing graded potentials, it might help get you to threshold when these positive charges reach that sodium accumulation. Downstream, you've got more voltage-gated sodium channels. They're in the state where they can be open. I didn't draw that. So, oh yeah, over here. So activation gate closed, inactivation gate open. These are at resting membrane potential. You can open them with the same amount of sodium coming in through voltage-gated channels downstream that initiated the action potential at the initial segment or trigger zone. The amount of sodium that comes in is more than enough that will trigger the opening of the sodium channels downstream. Once you open those and sodium starts to rush in, you get retrograde and antigrade, so backward, forward movement of sodium. The sodium that comes in the next part of the axon will open voltage-gated sodium channels downstream, and you get sodium coming in again. Diffusion upstream. Now you're running backwards to where there are voltage-gated sodium channels, not ligand-gated channels. Why doesn't another action potential get generated? Because when you're repolarizing, not all of your channels are back to their original conformation, and they can't be opened again. It can't be opened when the inactivation gate is closed. You have to wait until enough positive charge is pumped back out, leaving negative charge inside, to get that block, that part of the protein out of the channel. So as you get that out of the way and this activation gate closing again, you're going to be able to open that channel again. The number of channels that have progressed back to their initial state, you're reaching that somewhere in this lower part of repolarization. Some textbooks say by the time you get back to resting membrane potential here, all your channels, all your sodium channels are back in their original conformation. You can open them again. But you have to remember potassium is still leaking out. And when you look at what happens, the neuron will go past resting membrane potential, and then I'll draw it in green. It'll go past, and then it will come back up to resting. This, after, they refer it after the action potential, after hyperpolarization. That's due to potassium leaking out. So theoretically, the only time you could generate another action potential with the same stimulus that created this first one is that fraction of a millisecond where you're crossing the resting membrane potential and not having too few sodium channels ready to open and not having too much potassium efflux. The likelihood that that's going to happen at any time in the body is extremely unlikely. Most of the time, the sodium that is diffusing backwards in an axon is running into this after hyperpolarization. That means you actually have to recruit more sodium channels in that area than you did with the first action potential. And that would require a greater stimulus. And you don't have that greater stimulus due to voltage-gated channels opening downstream. So the only way you could get another action potential generated is if these other neurons created a bigger graded potential in the cell body. We'll come back and talk about that later, mostly in the neuron. So right now we've got to understand the movement of ions through the channels, what they do to the charge inside and outside the membrane, how you sum to threshold when you have negative charges and positive charges accumulating in the neuron. Yeah, if you have more positive than negative, simple math. Get to threshold, you get an action potential. Always going to be the same from the trigger zone all the way down to the end of the neuron. It's going to be regenerated at every point that you have these voltage-gated channels. You've heard of absolute refractory period and relative refractory period. Absolute refractory period is when you absolutely positively never can get another action potential generated in that segment of the axon. So absolutely not. Parents have probably said that to you. Can I? No, absolutely not. So it's hard, fast, no way you're going to do it. When is that occurring when all your sodium channels are already open. You can't reopen them if they're already open. So the rising phase of the action potential is part of your absolute refractory period. The relative refractory period is where if your incoming stimulus is larger than the one that made the first action potential, then you can get to threshold. So you have to try and figure out, and there's arguments, so where the absolute ends and the relative begin, you'll see textbooks say different things. Some textbooks say relative refractory period occurs when you get back to resting membrane potential, and you after hyperpolarize and then get back to resting membrane potential again. So relative period here, you have to make up the charge difference due to potassium leaking out. To make up that charge difference just to get back to resting membrane potential is taking more positive charge. You then have to get more positive charge into the cell body and the dendrites to make up that difference. And then you still have to get the same amount of sodium or positive charge in to get to threshold. So you have to have at least as big a stimulus plus a bigger positive or depolarizing greater potential out there in the cell body. Other people will say, well, you didn't recruit every single sodium channel there, so as long as you get some of them back into their original conformation with a bigger stimulus, you can reopen them. So you'll see some textbooks saying relative refractory period occurs or begins somewhere in here. So it has to be after the peak, and it will continue till you're back to resting membrane potential and flatline. That's your relative refractory period. Absolute is on the rising phase, and probably part of this falling phase as well. But where that ends and the relative begins, debatable. Ligand-gated channels, you've got graded potentials that are depolarizing and hyperpolarizing. These are also called local potentials. You also have local potentials occurring somewhere else in the neuron. Where is that? No. Well, jump and pull. Dendrites or axons? Okay, we had discussed dendrites here. Okay, so axon. Do you have, when you're operating voltage gated sodium channels and potassium channels, do you have depolarizing and hyperpolarizing local potentials occurring there? Yes. So you have them occurring here. You have a depolarizing potential that's in a segment of the axon due to sodium coming in. And then you get a hyperpolarizing potential due to potassium efflux. So the rising phase of the action potential is due to depolarizing local potentials that happen to open voltage-gated channels. Repolarization is due to hyperpolarizing local potentials. If you're still confused, Psych? What you need to do, and what every grad student has ever done, is draw this out probably 40, 50 times. Explain it to your mummies and your daddies and your dog and your cat and anybody out there in heaven. Just talk it out. If you rehearse it only in your mind, you're not going to get it. You have to be able to verbalize it. Then you're going to get it. So that's why you get your patient moms and dads to listen, or grandma and grandpa, somebody to listen. And if they start screwing up their face, well, maybe they're just not understanding the concept. That's okay. But if they're not understanding your sentences, that's a problem. That means you don't have the mastery of the material. So if you're saying, well, if this guy changes and then that guy changes and this happens in this area and then this is good to open that but not good to open that, people are going to go, what? But if you say a neuron releases neurotransmitter, binds to a receptor, it either lets positive charge go in and accumulates, keeps positive charge from going out, so positive charge accumulates, or decreases negative charge going in. But secret, there's an ATPase that pumps it back out. So since it's not coming in and you're pumping it back out, you're accumulating positive charge. Even mommies and daddies can understand that. If you can explain it coherently to mommy and daddy, and then come to me and explain it to me or to one of the TAs and get a, yeah, you're right, you got it mastered. Why do we emphasize it now? Because you got to use it for the rest of the year. So we're going to go into neurons, we're going to go into muscle. Muscle has diffusion, muscle has action potential, different kind of channels. So if you don't understand the channels that are this simple now, when you get to muscle, where it's more complicated, when you get to neurons, which is even more complicated, when you get to the endocrine system, where you've got all of these various types of ligand-gated channels and then voltage-gated channels combined there, you're going to be proverbially SKED. Okay, so you got to understand it now. Okay, graded potentials. Current flows. Current is flowing through a channel. Positive charge accumulates. Current is flowing inside because you don't let positive charge leave. Positive charge bumps against positive charge, repels. Current is still flowing. Negative charge getting pumped out, leaving excess positive charge inside. Still, positive charges are repelled by each other and move away from each other. That is current flowing. Graded potentials are degraded by the local current flow. That's why the graded and the local potential description are used interchangeably. Because the local current flow is causing the dissipation of the charge that was occurring when you manipulated the ligand-gated channel. So when you have local potentials that are moving towards a site where you can trigger voltage-gated channels, when you get to, if you get to threshold here, you generate an action potential. If, as the charges are diffusing away from each other, they dissipate enough that you don't get to threshold here, absolutely nothing happens. So graded potentials, short distance, if they're not reinforced by other charges, they simply disappear and you're back to resting membrane potential. So we got a little channel here, it's got a little divot on the outside. That's where your ligand is going to bind. So right now the inside of the cell is negative, out in the extracellular fluid, right across the plasma membrane, you have an accumulation of positive charge. Part of that is due to sodium outside, part of that is due to potassium normally leaking out through its leak channels. The negative charge inside the cell is primarily due to the large proteins that have negative charge on them that are too big to get out. So they stay inside the cell. A lot of these are your structural proteins that are keeping the shape of your cell. You don't want them to go out anyway. But there are other proteins in there that are just big globular proteins, and they can't fit through a channel, and they don't get exocytosed. So they're just there for the life of the cell. So at resting membrane potential minus 70, you have a net negative charge inside the cell, a net positive charge outside the cell membrane. To get depolarizing graded potential, you will have to cancel the negative charges, and you can do that by having these positive charges enter, or you can keep the positive charges from leaking out and the ATPase will pump them back in, or you could prevent negative charges from entering and the ATPase is pumping free negative charges out like chloride. So to open that channel, you need a ligand. You need a neurotransmitter. So we have the neurotransmitter bound to the protein, that's the channel. The channel opens, positive charge is leaving the outside and diffusing inside the cell. Notice charges are diffusing both directions. So some of them are going to the right, some of them are going to the left. What is going to, but as they diffuse away from each other, these two charges, as they get further away from each other, they have less of an effect on the inside of the cell. So you have, you may start out with positive charge coming in, but as the charges diffuse away, you'll go back to the negative, towards the negative charge inside. Also, these positive charges could run into an ATPase that pumps them back out. Another way to lose them. So either you lose their concentration due to diffusion, or you lose the particle due to the ATPase pumping them back out. What you have in this section is a graded potential. It is localized. It has no effect to the right. It has no effect to the left. So it's referred to as a local potential. It's graded because, like grades, they're either high or they're low. And they're low in graded potential because the charges are diffusing away from each other and also being pumped back out. So what do the positive charges do when they come in? They're going to cancel the negative charge that was inside where they're located. They can diffuse to the next segment and cancel some negative charges there. As the positive charges enter, they're disappearing from the outside, which leaves you less pluses on the outside. So now the outside of the membrane is becoming negative. Where the positive charges have left, the outside is negative. Where they came in, they're positive. These positive charges now aren't being repelled to the right or left by the positive charges that entered, so they can diffuse into that area. And that's what these arrows are showing you, that these positive charges and those, they're all going to move away from each other because positive doesn't like positive. So they're going to spread out and move towards the channel. It looks like the channel is closed. Go back. Yep, this big triangle is no longer there. The big space is no longer there. So the channel's closed, the ligand is gone. Why is the ligand gone? Because an enzyme broke it down. Or it diffused off the active site. So one of the two. The positive charge inside, again, diffusing and canceling the positive charge next door. As it's doing that, it's losing its overall cumulative effect. And it might be running into an ATPase that will pump it back out. So the spread of these charges helps with the dissipation of the charge. The spread of the charges where you only have ligand-gated channels will have no effect on them opening. You have to have a ligand bind outside in order to open the channel. You can't turn a ligand-gated channel into a voltage-gated channel. They are separate operations. So direction of current flow, site where the charge came in was minus 70, but then it went to minus 55. Minus 55, the positive charges diffuse to the right and the left. And so 50-50 diffusion each direction. The area next door is going to have less positive charge moving into that area. So the adjacent areas don't go to minus 55 because there's less positive charge going to those regions. They only go to minus 60. So you're more negative. Minus 55 in some neurons, that's threshold. But already you've just diffused a few nanometers to the right or the left, and you're subthreshold already. You go a little further, you're even more subthreshold. You go a little further, you're back to resting membrane potential. So if that was the whole magnitude of your local potential, and it didn't even leave the dendrite and get into the cell body, nothing's going to happen. It's got to have enough positive charge that's moving all the way from the dendrites to that trigger zone, or nothing's going to happen. So when you look at the decrease in positive charge over distance, the area where you open that ligand-gated channel is going to have the most positive charge. So you look here, the change in membrane potential in millivolts. You've gone from well, it's a little bit, just look at the absolute change in the charge in the area. This says 0, but that is super threshold, so it's a little confusing to me to read this graph. But if you look at just the concentration of the charges and look at the absolute charge, and not try and relate it to resting membrane potential at this point, but look at what would be left to help to move resting membrane potential towards threshold. You have a lot of positive charge there at the site of the ligand-gated channel opening, but as soon as you go in either direction, the overall amount of positive charge, you went from 15, and then short distance later, you've only got 10 millivolts. And then you go another short distance away, and you're down to 5 millivolts. And then if you go far enough, you're at 0 millivolts. So absolutely no effect on resting membrane potential. So these increments here are the millivolts that you can add to resting membrane potential to get it to decrease towards threshold, to become less negative. So too far away from the point of entry, you've got no help in getting to threshold. At the site of entry, you may get to threshold with this 15 millivolt change. in charge. But to either side, you're already below threshold, and the further away you go, the further away from threshold you get. Okay, so threshold potential is going to be different in not every neuron, but in a lot of different neurons. It's going to be different in different cells. So don't be bent out of shape because right now you're told that threshold is, well, one slide said minus 50 and this one minus 55, so that's already different. I heard that Robino tells you it's minus 60 if you had his class. Take minus 55 and round it up. Round it down, you get minus 60. You take minus 55 and round it up to minus 50. Plus or minus 5 millivolts. You got all those different thresholds. So nobody's wrong. It's just they're looking at it from round up, round down. No, I'm not going to round up or down. I'm just going to take minus 55. Other cells will be very different than that. So the more you get into excitable cells, the more difference you're going to find. So right now, relax and enjoy the differences because they're only going to get more different as you go along. So you have to sum what's happening to sodium and potassium. And in the back of your mind, you can think about chloride. Remember that chloride can move too. It's going to be more important when we get to later chapters. But we want to take the resting membrane potential from minus 70 towards the threshold. Get to threshold, it's going to automatically open the voltage-gated sodium channels and you'll go almost directly towards plus 30 in just a millisecond. A whole action potential is usually over in less than a millisecond. So from reaching threshold and back to resting membrane potential after the whole thing is less than a millisecond in time. So really fast. When you get to threshold, and you reach plus 30 and back, you have just created the whole action potential. Action potentials can't be bigger and smaller. They have to be identical in every segment of the axon. And however long it is, it has to be regenerated and then propagated towards the end of the axon. So that's why action potentials are described as all or none. You either get one or you don't. You don't get one if you don't get to threshold. You do get one and you get all of it. You don't get less or more. You're above threshold. You don't get a bigger action potential than when you're just reaching threshold. You get the identical action potential. Okay, take a break.